Starting a new unit, some of what we do in this unit is, especially today, is related to what we've been doing. And then starting tomorrow, it's a little bit different, but a lot of the skills are the same. So that stuff we've been doing with factoring is a big part of this unit. So that part doesn't go away. So let's get into it. This is something, again, from grade 10. Recall the zero product property. And in grade 10, we're just doing quadratics. So it's just like you have, two binomials multiplied together, and that product is 0. What can we deduce? Logically, one of them has to be 0. And we use that concept to solve quadratic equations. When we solve a quadratic equation that way, we may have to factor it to put it in that form. And if we factor it and put it in that form, then we can use zero product property to sort of for one next step and then solve and actually find the answer. What is solving an equation? It's interesting. It's, this is something you do in elementary school, and you do it a lot in grade 9, do it a lot in grade 10. And hopefully every time you revisit it, you kind of take a moment and step back and think again about what it is you're actually doing. Because it may seem trivial, but as we make more connections in math and we grow in our understanding in math, even thinking about those little things and reminding ourselves about them, I think, you think about it in a different way. You reflect on it in a different way, and it can help us tie things together and get a better perspective on things. So what is solving an equation? Well, it's finding the value of the variable that makes it true. We did this in trig, and we talked about it in different ways. But basically, when I look at that first example, there will be one or more values that will make that statement true. Left side equal to right side. Okay? And so we want to find those values, essentially. That's what solving an equation is, right? And this is just skills. Like, why would we do that? What's the point? Well, that's when you have to have context. You have to be doing some kind of application, or the equation has to represent something. Then it has meaning. When we're doing it like this, it's just practicing skills, right? So we're going to use the zero product property again with all polynomials. It's the exact same idea, if you haven't figured that out yet, as a quadratic, except we'll have more brackets probably. But the same thing, we have to split it up into a big product of multiple things equal to 0, and then we can use the zero product property. If A times B times C times D is 0, then it must be true that the only way that will be true is if one of those things is 0, right? That's the idea. And then heads up, the discriminant, b squared minus 4ac, tells us the nature of the roots of a quadratic. How is this different in this changes today? We didn't do this in the last unit, but now we have to bring this back in, because in the last unit, if you got down to a quadratic, but the quadratic wasn't factorable, you're done, because your instructions were to factor fully. So we get it down, maybe you started with degree 4, so you pull out one bracket, you pull out another bracket, so you've got x plus 1 times x minus 2 times a quadratic. If that quadratic wasn't factorable, which it usually was, but if it wasn't, you were done. But now we're solving. When you solve, it doesn't matter if that quadratic is factorable or not. That's not the case. We're solving. So if it's factorable, factor it. If it's not, you have to use the quadratic formula to keep going. Okay, so let's try this first one. Stop me along the way if you have any questions. Otherwise, we're going to truck forward. We've got a whole bunch of examples to do. We'll get through as many as we can. Does anybody notice anything about this one? So it's degree 3. All the terms are there. If I was to use factor theorem, I would look for something that, again, I would look at this like, well, those two are both negative. But if I can make one of them positive, that will be 0. And if I can make one of these positive, that will be 0. So it looks to me like -1 will work, right? You can look for those kind of hints. But what else do you notice? Does anybody notice anything else about this one? Yeah, we can factor this one by grouping. So I'm going to comment, if you don't notice that, then you can do it the other way on that test that just got handed back. There was a one question that was factorable an easy way, so it was only worth 3 marks. And a lot of people didn't do it that way. They used factor theorem. It took you a lot more time. It's a lot more work for 3 marks, but that's factoring, right? And that's problem solving. That's math. That's all areas in a lot of ways. If you don't notice the easiest way of doing it, it's going to be harder, right? But there's multiple ways of doing it, so you do what works. So I'm going to factor out an x squared, and I get x plus 1. And so what is the point of factor by grouping? I need to factor the second 2 terms in some way so that I have a bracket that's x plus 1. So I'm going to factor out a minus 4, and I get x plus 1. And this is still all equal to 0. Whoops, this equal sign shouldn't be there. Always, people forget that. You will lose a mark. It's always equal to 0. That's another thing. It didn't happen too often, but on the test a few times people had like random equal signs. And I said, like, equal to what? What are you talking about? Like, it's really important, and the harder the math, the older you get, the more we're going to demand that what you're writing makes sense. Things that you might have gotten away with in elementary school or grade 9 or grade 10, you're not going to get away with for as long. So things like saying things that are equal when they're not, my goodness, that is a huge part of communication in mathematics. So keep that in mind. And when we're solving equations, we always write both sides of the equation, right? So don't forget that. That, to me, that's just habit. People start going fast and they forget to do it. Something you could check. Go back after you've finished your quiz or test or whatever and check that you've done it all. So then I write the first bracket and x squared minus 4, the things that are multiplied by each bracket. And we're not done because that second part can still be factored, x plus 2, x minus 2. And now we're done. Are we done? We're not done. Why are we not done? Because it says solve each of the following. It doesn't say factor fully. We're supposed to solve. So what does that mean? Again, using the zero product property, it's important to say therefore at a statement like this, because to me, whenever the line, like every one of those lines, I was just doing algebra steps, but I was changing what was in the line above, just using some kind of algebraic fact or strategy or formula or whatever, factoring in this case, right? And changing every step, but every step was kind of equal to the one above it. All of a sudden, we're writing something different. Like our next step isn't a direct algebraic manipulation of the step above. So that's when we would use a symbol like therefore. I can deduce, therefore, because of zero product property, x plus 1 is 0, or x plus 2 is 0, or x minus 2 is 0. And that means x is negative 1, x is negative 2, or x is positive 2. Yeah. You don't have to do both steps. Everybody got that one okay? What's different about this one? Yeah, the terms are on both sides. So what does that mean? Do we solve it a different way, Jason? What do you think? We can move everything to the other side. Folks, I'm going to give you a hint. This is always what you do. Okay, there's like one special case where we don't move everything to one side and set the other side equal to 0. If you're going to use the zero product property, people take this for granted. We get in habits. We forget why what we're doing works. We forget why we set it equal to 0 and we factor and we get all these different things. And when you forget why we do that, you start using it in places that you can't. Okay, well, I'm going to show you another example of that, a really good example. This one's not so much a problem for people. There's another type of question that's a major problem. People do silly things. Okay, so I'm going to point that out, but like you have to set it equal to 0. So we're just going to move everything over to one side. 2x cubed minus x squared minus 7x plus 6 is equal to 0. Now what do? We factor. So go ahead and do that. I want you to try this one on your own. It's more good practice. Notice that this is no longer f at x. So if you're using factor theorem, you've got 2 options. If you like the notation that we were using in the previous unit where it's like f at 1 equals 0, therefore x plus 1 or x minus 1 is a factor, you have to first say let this equal f at x, because it's not. Just like we were doing let g at x equal this, right? So let f at x equal this, and then use that notation. Or you could do it like off to the side in scrap or something like that. And if you're doing synthetic division, again, I would absolutely do it off to the side. Even if there's not space, then I would get scrap paper or something. Okay. Or you can drop that step and just write the factor. And if you're doing synthetic division, still do it off to the side and just start writing the factors. If you're not sure what that means, I'll do it and you'll see. So go ahead. Monsieur, what factor did you find? X minus 1. Saw a few other people who got that. So that means positive 1 gives you 0, right? That's 2 minus 1 minus 7 plus 6. So I've got 8 positives and 8 negatives. So that's 0. That was hopefully an easy one to find. Kind of looked to me like it might have worked just at a glance. And then there's the, so see how I wrote it? I just factoring, just write next step so it flows nicely. And I use a little trick to find the quadratic, and the quadratic is factorable. So I've got this far, and I know that these two are going to be 2x and x because 2 is prime, so that's the only thing that's going to multiply here. Yeah. Yes, thank you. And so then I whenever I get a prime, I like to put those in. I think we talked about this, but just a reminder, some people might not have liked this last year, the year before, but now you're getting better with your algebra skills and you can do things a little bit more quickly. And this looks like it's going to be 2 and 3 because it's 4x minus 3x, so I want this to be positive and this to be negative, and this is equal to 0. Therefore, x will equal 1. I'm going to do this the long way again. Just because people love skipping steps and people always want to, try to do things as quickly as possible, which is fine as long as you're getting them right and as long as you really understand it. As soon as you make a mistake, you want some method, some step, something you can fall back on that will slow you down, that will structure it to make sure that you get things right. So writing out that step is what you could do. I move the 3 over, it becomes positive, then I divide by 2. That means x is going to be positive 3 over 2. Some people throughout this whole unit will get that wrong. Even though you'll do it on a learning goal, I'll mark it wrong, and then you'll keep making that mistake. You'll do 2 over 3 instead of 3 over 2. My goodness, we got to get that right. Yeah. Why would it be that? So why would it? But why would? But this is an important question. Like, I don't know. Maybe you're right. How do we figure it out? Like, how do we decide who's right? If two people are disagreeing, what do? Expand it and see which one works. Try it both ways. This is kind of a guess and check process. I always put the signs in last, and in my head I expand. So this is what I would do. Now it's a little bit different from a simple trinomial, because with a simple trinomial, the bigger number shares the middle sign. But because this is a product, it's different. There's the 4, and there's the 3. I want the 4 to be positive to match the middle, so I think my signs are okay. But that's like, that happens all the time, even in my own head. I'm like, is this right or is the other way right? How do you do it? You expand, figure out. Does that make sense to you? Do you like that okay? I think the signs are okay. Positive 4x minus 3x. I want that middle term to be positive, so I think I'm good. Any other questions? Okay, let's keep going. Where's my next example? Any common factors in there? No common factors. 3s, 5s, 15s kind of looks like maybe there's something going on, but there isn't. Always makes your life easier if you can do a common factor. Also, if we can common factor something out, like a constant, like a 2 or a 3 or a 5 or a 10, because this is an equation, we could divide both sides by that number and get rid of it. We don't have to hang on to it throughout the whole process. We just get rid of it, which is awesome. You may never divide by x and get rid of an x. This will come up throughout this course, and I will remind you, but I'm telling you right now, never, never, never may you do that. Okay? X's don't cancel and cross out like that. Okay? Can't divide both sides by x. Like if there was an x in each term, it doesn't just disappear. Never, 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 never. Okay? In grade 11, when you simplify rational expressions, you do. You cancel out an x plus 2 and an x plus on top and an x plus 2 on bottom. You divide them to 1, right? And we'll see that later in this course, and I'll tell you again that you're not allowed to do that and why. And sort of sometimes we do it, but with like a careful check of when we're doing it. Anyway, but for now, if that ever came up, just so you know, don't do that. That's something that some people do. Okay, but go ahead and start working on that. Does anybody notice anything to get us started on this one? I noticed 3. Oh, Monsieur, were you going to say something? Maybe, because I noticed that 3 and 5 and 7 add up to 15. So I'm thinking, See how these little things that you just observe, that gives you an idea. I should check that carefully. Okay, go ahead. Yep, x minus 1 worked. Get a quadratic left over. What should we do with this quadratic? How did you figure that out? So something like that, use the discriminant, it worked out to 148, okay? You don't have to state this, but for yourself, you might want to. Okay? You might want to write it down just to remind yourself what you were doing. It can help you find a mistake if you end up making a mistake and you go back and look for it later, right? There's all kinds of reasons. 148 is not a perfect square. Therefore, this is not factorable, but it's certainly solvable. Now, here's something else that I want to talk to you about. The homework talks about solving even when it's imaginary. So if this worked out to a negative, it's solvable it's not solvable in the real numbers, but if we go to imaginary numbers, you can solve anything. So you would have to continue and do that. There's only one question in the homework that comes up that way. So I would encourage you to try it. I don't think we're going to do an example like that in our practice, but I would encourage you to try that. It won't come up a lot, but it's something to think about where equations have answers depending on what numbers you allow. Okay, so your instructions might say in the real numbers only, or they might say it'll be an element of it'll be like a C like this, right? Like a double bar C, what we call that. So that means in the complex plane is what that stands for as well, and that means imaginary numbers are okay, and you have to include them. So if you get a negative, it's going to tell you what your answer is going to be like, but it doesn't mean stop. It means keep going, okay, depending on what you're supposed to solve for. We'll talk more about that as we go. Something that's very interesting, it's called the fundamental theorem of algebra. It states that for polynomials, degree 3 polynomial has to, this was proven years and years and years ago, absolutely 100% has to have 3 solutions. 2 of them may work out to be what we call non-real, but it has them. They exist, okay? So so a degree 7 has to have 7 solutions. But again, some of them might be non-real. And there are these really, really interesting little, we're not going to get into them today, but demonstrations that show you why that has to be true and all kinds of things. It's really interesting. There's a really good video series. I might post it to the classroom. The first video is really, really, to me, really interesting. And then if you like it, there's like a whole bunch more that you can watch. They're only 5 minutes long, they're short. But it's really interesting stuff. It's really easy to understand, but really makes you see that math like has all these interesting aspects to it. The fact that, I'll give you a little taste, the fact that they are called imaginary numbers is a huge disservice to them. They're not imaginary. They're not. They exist, but they're a different way of thinking about numbers than the way we generally think about them. We think about the numbers, real numbers have to be in a single number line, and that's just not true. That's a made up idea. When numbers were first invented, they were only used to count things. So only countable numbers, the natural numbers, existed. Those were the only real ones, starting at 1 and up. Because like cave people only cared about how many rocks they had. So all they needed to know was 1, 2, 3, 4, 5, 6. The number 0 didn't even exist for thousands and thousands of years. Cultures didn't have an understanding or a representation, a symbol for the number 0. And they got more sophisticated. 0 only started as a placeholder for a number like 10. It wasn't even its own number. And then 0 came, and when negative numbers, people started exploring negative numbers, mathematicians at the time thought they didn't exist. And they're like, that's ridiculous. All the math you ever need can be done with, like, they didn't have words for it, but positive numbers, positive integers. We don't need negatives for anything. And then, of course, over time, now we realize how important negative numbers are and how obvious it is that there are negative numbers. But back in the day, people didn't think that was true. And it took a whole generation for people to sort of realize, like, okay, yeah, this is actually a thing. Negative numbers are just as real as positive numbers. And now they're like a no-brainer. And the same thing happened with what we now call, unfortunately, imaginary numbers. They're not actually imaginary. There's just a different way of thinking about numbers. But they totally exist. They have to, because of the fundamental theorem of algebra. Anyway, okay, tangent. So what were we talking about here? So we have this, x equals 1, and x equals, I'm going to write this down once. I'm going to write down the formula. I've seen a couple of people get the quadratic formula wrong. Oh my goodness, you can't afford to do that, especially in this course. So make sure you, if you haven't memorized it yet, or you have to re-memorize it because you forgot it, make sure you do. Okay, it's not going away. So, but normally I probably wouldn't write it because again, it kind of interrupts our flow. But it's negative b plus or minus the square root of b squared minus 4ac all over 2a, where a equals 3, b equals 8, and c equals negative 7, right? These coefficients from the quadratic up here. I'm going to add my therefore. I forgot I should put that in. But again, see how like I get to a line, and then from that line, in the examples above, I was saying therefore x equal this, this, and this. I'm doing the same thing. Just in this case, one of my x equal statements is like longer and more complicated, but it's the same idea. So I've factored it. That's as far as I can go with that. Therefore, my next step of this process is this. One side's done. That's done. This side we're going to continue with. So negative 8 plus or minus. But what you should do, absolutely, is this step where you sub in once. Like show the full substitution step. This is what I would do. And I would do this because then you can find a mistake if you make one again and go back. And it's kind of a thing that when we substitute, we don't do any work in the substitution step. Okay, and then this worked out to 148 over 6. And then we're going to reduce, but we're going to keep exact answers. And again, this depends on instructions. You should always reduce, but if you're asked to do a decimal in your last step, then put a decimal answer around it, whatever. Okay, but you should always reduce these answers as far as possible. Keep them exact as long as possible. How do we reduce 148? We're looking for a perfect square factor, something that divides into 148. That is a perfect square. 4 does. Anything bigger? How could you find out if there's something bigger? Well, I would, go ahead. Yeah, I would divide it by 4, see what's left. And what's left may have another perfect square factor or may not. If it does, I would go back and figure out what the bigger one was. If it doesn't, so in this case it's 37, so that's prime, you're done, right? So that equals negative 8 plus or minus. So we took 4, so the square root of 4 is 2, so I pull a 2 out front of 37 over 6. And I can divide 2 out of all 3 of those parts. Put your pencil down and watch. This is hard. There's different ways of showing this. I can show you another way if you like. But essentially, we've got 3 things. There's 1 plus, there's another, and there's another. We're dividing 2 out of all those things. I don't divide 2 out of that. It's inside a radical. You can't, that's totally different. You can't pull it out, right? We're not doing that. That's why we already pulled the 2 out. So this is going to be negative 4 plus or minus root 37 over 3. And I'm going to split it up into 2. X equals negative 4 plus root 37 over 3, and x equals negative 4 minus root 37 over 3. And I think you can do the next part on your own with your calculator if you're asked to. 2 decimal places, 3 decimal places, whatever. Don't do that earlier and round and keep decimals down the way. Oh my goodness, no. Keep it down to the very last step like that. Reduce it as much as possible. Again, this is a big part of getting better at mathematics, is getting used to work. Some people don't like it. Well, you took the wrong course. Like in this course, those are the kinds of things we have to do, right? Everybody okay with that? One more. Well, there's a few more, but let's try this one again. This is the kind where folks, oh my gosh, people mess up and they do something different here. Oh, this one's different. Maybe I can solve it a different way. No! None of these are solved in different ways. Okay? They're not. They're sort of one, like I said, they're sort of one kind, but like when that comes up, we'll maybe talk about that a little bit tomorrow or the next day. We'll do a fun little thinking activity about it. But like otherwise there's no other ways of doing these things. And the other kind is a totally different kind. Like it looks totally different. You'll recognize it. What do? People are like, oh, this is already factored. Perfect. It's easy. So then what? Either this bracket equals negative 18, or that bracket equals negative 18, or that bracket equals negative 18. If you think about what the zero product property is and how we use it, it's absurd to use it about any other number. The product of these three brackets is negative 18. Those brackets could be anything. I mean, they could be 3 and 6 and 1, or 9 and 2 and 1, negatives, positives, something like that. Like, you could guess at what they might be, I guess. That's not really going to help you anyway. But it could be like 1 over 18, 18 and 1, or like it could be anything, right? Our answer could be anything. So this tells us nothing about what our answer is going to be like. So what do we have to do? Unfortunately, we have to expand this whole mess, bring the 18 over, set it equal to 0, refactor it. There's no other way. You can't just bring the negative 18 over, because then you'd have three brackets and a constant, and that won't work. The only way we can do this, it's a disaster, so much extra work, I know, but that's it. You have to. Right? So you won't, I mean, on a test or whatever, you wouldn't get that many questions like this, if any, but that's the only way we can do it. So let's start doing it. And there's no rule, I'm going to try to do it the way that makes sense to me. So 2x plus 7, why am I leaving this one? Because this is easy for me to expand without any work. It's going to be x squared minus x minus 2 plus 18 equals 0. I'm going to do that right now. And then I multiply this through. Oh, and watch. You might, I think, oh no, not equals. I think you want to watch this. So this is going to be 2x times x squared is 2x cubed. And now we can use that trick that we were using to factor, we can use it to expand. Two terms will be x squared terms. This is 1 and that's 1. And for every step that will happen. So I don't have to show that step. And I don't want to, because it's a lot of work and it's a pain. And it's going to be like this huge expression that's going to go off the page. You know how in grade 3, then you start like writing down the side of the page to try to, we don't want to do that, right? That's hard to read and that's a mess. So as much as you can, try to get it all done. So that's 7x squared minus 2x squared is plus 5x squared. That being said, if you're not good at keeping some of this stuff in your head, you might be likely to make a mistake. And in that case, absolutely just make sure you got lots of room and write it out. Okay, and then what's the next one going to be? It's going to be my x terms. So one of them will be there and the other one will be there. So negative 7x minus 4x is negative 11x. And then minus 14 plus 18. I could have done all that in one step too. In fact, I'm going to, right? So I'm going to make that positive 4. We okay with that? Two plus 5 plus 4 is 11. Minus 11 is 0. So again, it looks like if I just plug a 1 in there, I get 2 plus 5 minus 11 plus 4, so that works out. So that means I've got x minus 1. So this is how I do. I'm going to run you through this again. If you want to put your pencil down and watch, it might be a good idea. If you're still doing synthetic division, it's fine. I'm not trying to talk you out of it. I'm just saying there is a faster way, right? Just could zoom in a little bit more. So I know this is going to be a 2x squared because those are the only terms that are going to give me x cubed to give me 2x cubed. And then what do? This gives me negative 2x squared. I'm looking for 5x squared. What do I add to negative 2x squared to give me 5x squared? 7x squared. So this times that, whatever is going to be, has to be positive 7x squared. So if I make that's a lot to keep in your head, I know. If I make this plus 7x, and then I do a quick check, 7x squared minus 2x squared is 5x squared. So it works. Okay, and I do the same, and then my last one is just a constant, so it's going to be minus 4, because negative 1 times negative 4 gives me positive 4. But I can check that 7x as well if I want to by doing another multiplication, right? Negative 7x minus 4x gives me negative 11x, so it works for both, so it's got to be right. And then let's see, what are we going to do next? You want to practice this enough so that you don't have to stop and think at every step. Like if you have to think for a minute, what do I do next? You want to dive in, discriminant. You're going to check the discriminant. So b squared, b is 7, so 49, and then minus 4ac, but c is a negative. So I'm going to have 2 negatives, so it's going to be positive. So I'm actually going to do plus 4 times 2 times 4. I got 81. What does that tell me? It's factorable. Perfect square factorable, way faster, way less, takes up less space on my page than the quadratic formula. So I'm going to do that. And again, it's 2x squared is prime, so I know it's 2x times x. And I think it's going to be 4 and 1. So 2 times 4 is positive 8 minus 1 is positive 7x. And negative 1 times positive 4 is negative 4. With a little bit of practice, you can get very fast at this. And that's what you're aiming for. People work at different speeds, but with practice, this is like a skill you just want to be quick at. It's like imagining if it took you 30 seconds to figure out, what 3 times 4 is, how would you ever finish a test? Right? Was this like, but 3 times 4 used to be hard for you back in grade 3, right? That was something you would have to spend some time thinking about. Even if you're good at math, it would take a little bit of time because you were just learning it. But then you got to get better at it. Same thing with this. Any questions? We got a few more. We're going to keep going. Oh my gosh. Let's do this one. There'll be little things that come up. We're just practicing. We're doing a bunch of examples but you can go ahead and do it, is my point. But like, if you like to watch somebody else modeling how you do this and you like to see it over and over again, if that helps you, then I'll keep doing them. But really, at this point, I want you to try it yourself, and we'll follow along together and see how we do. That being said, this is the first example we're doing that's degree 4, but there is something about it that you want to notice that's going to help us. So look carefully. And then go ahead and try it. So what was that good thing to notice? That there's a common factor of x. Which reduces our degree, makes it a lot easier to factor. Like we don't have to factor as many times. Well, we factored once there, but we don't have to do like factor theorem as many times, right? So it makes it a lot easier. I found x plus 2 as a factor. Divide it out. How many other people found that? Very good. And then what's left? What did you figure out about that? Anything? Like, what should we do next? Again, you want this to start becoming automatic, so I kind of know I've got two options. It's either factorable or it's not, and I would use the quadratic formula. Can I factor this? I can. B squared minus 4ac was 49. In fact, we didn't write that down before, so I'm going to write it down this time. C equals 49, therefore factorable. So in this case, 6x squared is not prime, but the 3 is. So I'm going to go with the 3, right? I'm going to write down the 3 in there and then look for a sum of 11. And I know 3 times 3 is 9, and 9 plus 2 is 11. So 3 and 2 are going to be my numbers, and everything's positive. So then again, you can do an extra step here. But therefore, I've got 4 things. Degree 4, what did I say? We'll have 4 solutions. 2 of them might be imaginary, might be in the complex plane, we call that, but they exist. But I'll have 4. But in this case, all 4 are real. So I've got 4 answers. Don't forget this. This is a step that people forget, okay? They forget to do this. They get caught up in the factoring because even if you weren't the best at factoring in the last unit, you're probably going to get really good at it if you practice especially. This is just more practice. We're going to do a lot of it. Then we forget to actually state the solution. The whole point is we're solving. Therefore, x equals 0, x equals negative 2, x equals negative 3 over 2. Don't get that one upside down. And x equals negative 1 over 3. And if I wanted to check any of those, I could take it and plug it back into the original formula, and it better give me a left side, right side check that works out. Okay? Any questions? I want to go by, I'm trying to think of what the best thing to do next is. Okay, we're going to do this one. But the next examples, again, I'm just pointing out a couple of interesting things that may or may not help you along the way. So this one is interesting because it really highlights something that we talked about in the last unit, and I want to just dive into that a little bit more. And it's not something that you need, like I said, you don't need to worry too much about this, but I think it's important to at least point out and talk about. 6 plus 8 plus 7 does not even come close to 41. Do you agree with that? So 1 or negative 1 will not work, because 1 and negative 1 means you're just adding up coefficients. There's no way to make 1 or negative 1 work. And I know just by looking at the 7, I hope you know this too, we talked about this before, but 2, 3, 4, 5, and 6 all won't work. Don't waste your time trying those, okay? They will not work. Because I would have to have like an x plus 2 and a something and a something, and these 3 things would have to multiply to 7. 2 doesn't multiply into 7. So these numbers have to be factors of that. Except not quite, there is a little bit more to it. But what I want you to do, I want some of you to try positive 7 and some of you try to negative 7. Quickly, go. Try it for me. Harder to do in your head because 7 to the 3 times 6 is kind of... And it worked? Positive 7 gave you 0? It didn't. Did somebody do negative? And it did work. So negative 7, anybody else confirm that? Yeah, nice. So that means x plus 7 is my factor. So if you want to just, like, I'll do this so that we do it quickly because this next part isn't really the important part. This is interesting. 7 times 6 is 42x squared, so minus x squared gives me that 41. And then I've got positive 7 and negative 7, so this is going to be negative 1 equals 0. Okay? But 1 didn't work. Like, what's left to be my factors if 1 didn't work? What else could there be? Right? 7 times 1 times 1 gives you 7. So don't the last two have to be 1? So this is the thing that it turns out, okay, so this is going to be 1, and this is going to be 1. They have to, because 1 times 1 is 1. And one of them is going to be 3x, and one of them is going to be 2x, and it's going to be negative 3x plus 2x to give me negative 1x. Therefore, x equals negative 7, x equals negative 1 over 3, and x equals positive 1/2. So we did this several times throughout the last unit. If I put in 1/2 to this, I would get 0, right? That's what it means to be a factor, to be a solution. Well, when we, like in the last unit, we thought about it in terms of factors, but in this unit, we can think about it in terms of solutions to the equation. If I put in 1/2, it better give me 0, because that's what the equation says, right? That makes sense. But like, so 7 worked for us. What if it didn't? What if we tried 1 and negative 1 and 7 and negative 7 and none of them worked? All your factors were fractions. It's possible. We don't really give these questions, but in the real world, it's possible that would happen. I don't know if you want to write this down. You can, or you can get it off the note later. But it turns out there's a little bit more to it. In fact, all factors that you could possibly try in terms of factor theorem are not just the factors of the constant, but they're a combination of where they have to be the form m over n, where in this case, m are the factors of 7 and n are the factors of 6, where 6 is the leading coefficient. Because those are going to actually turn out to be all the possible, exhaustive list of all the possible factors. Okay? So, and you can think of nx minus m as a root. Now the positives and negatives, we don't like, you got to try both, so we don't worry about that. But you think about these brackets, okay? So what would the list be in this case? If m is 7 and n is 6, well, the factors of 7 are 1 and negative 1, so plus minus 1 and plus minus 7. And the factors of 6, plus minus 1, plus minus 6, plus minus 3, plus minus 2, and all the combinations of those. So 7 over 1, 1 over 1, well, those are the ones we already tried. But what about 1 over 6, m over n? So 1 plus or minus 1 over 6, plus or minus 1 over 2, plus or minus 1 over 3. That was one of our solutions. Okay, and so on and so forth. 7 over 2, 7 over 3, 7 over 6. That would be a list. Be a long list and a real pain to do all those. That's why unlikely that would happen, but it's possible. I could see maybe trying 1/2 at some point and see if that works. Does that make sense? Any questions? That was a lot. We're almost done. I got 2 more examples. I'm going to give you one to think about. The other one we're not going to get to. But something interesting pops up in C, which we skipped at the very end. So it's going to take us too long to get there, but I'll put it online. You could try it yourself, see what happens. And because we're solving now, again, we can't look at these results the same as we did in the last unit. We got to think about the solution. So that's what happens in C. I want you to think about this. If I had 2 graphs, that blue graph is a parabola, okay, and there's its equation, it's g at x. And the green graph is a cubic, I can see by its shape, and it's f at x. What if I wanted to find the point of intersection between those two graphs? That sounds like something that's hard, because in grade 10, we find the point of intersection of two lines. That's it. Two straight lines. They could cross once or 0 times or infinite times be the same line. And now all of a sudden I've got quadratics. There's all kinds of options for like when we up the degree. But it turns out this isn't that hard. Don't I just go f at x equals g at x, move everything to one side and solve? That'll find me. Think about this. We're going to do more of this. This is something to think about. But so it end up looking like that question right there, B, or B above, both of those kind of thing, right? This is where cubic meets a linear, and they cross 3 times. We found all the x values. If you were finding the points, you'd have to sub in and find the y values. Anyway, something else to think about is the graph and how this relates to the graph.